So, good morning, good afternoon, good evening. So, since we are broadcasting to all of the world, so my name is Joan Lopes. I'm full professor at University of Porto and also associate director at INESC TEC. And I have the pleasure today to moderate this webinar where we have two guests, Professor Vladimir Miranda and Professor Joan Bosco. So I would like to start by just presenting you the concept of this webinar. So INESC TEC, through its Center of Power and Energy Systems and the Energy Cluster, has launched the Power and Energy Webinar Series initiative. So what we want, this is not a teaching webinar, this is very important for you to understand. What we want is to present and discuss ideas, expected outcomes, results regarding the energy systems of the future. And so, in fact, what we want is to share with the scientific and technical community the last advancements and the new vision for the energy systems of the future. Next. So, if you want to present a webinar with our team, so we have here how to do it. So please send us an email. We will analyze your email and contact the INESC researchers who work in your areas. Our researchers will then contact you for you to prepare the next webinar, and you are on board. Welcome. So if you will want to attend the next webinar, you just need to visit our website. Please click on the next webinars and find out more about future initiatives. Submit your participation in the participate section, and we will send you an invitation to your email. So I will now start by introducing you the first speaker. The first speaker is a well-known person in our scientific community, Professor Vladimir Miranda. He is president of INESC PMU Brasil. He's associate director of INESC TEC in Portugal. He is also full professor at University of Porto. He's IEEE fellow, IEEE distinguished lecturer. He is scientific advisor of several institutions. You can read them on this slide. And it is my pleasure to introduce him and to invite him to start. If we were presentially, I would tell him the floor is yours. Since we are doing it in a remote way, Vladimir, the screen is yours.
Hello, good day or good night for everybody, my good friends. I'm going to share my screen to start my talk. And I would like to underline the words of Professor Lopes. This is not a teaching webinar. So we are going to share with you our visions, our ideas, and perhaps provoke you into some discussion. I hope so. So let me share my screen. It will be screen number 2. Share. Okay, and then now. Yeah, here we are. And hopefully you are watching my presentation slide. Today we are going to talk, we have two presentations and they are connected, and we are going to address the problems of the awareness about the state of the system, or state estimation if you want. And my first presentation is about a new paradigm for dealing with gross errors and missing information, even in cases that previously were thought not possible to be calculated. So this is the good advancement. Nowadays we are facing a tremendous and amusing challenge, which is we now are flooded by a tsunami of data, In the past, we had models, models derived from theories, and the theories were based on our knowledge, best knowledge. And today we have the opposite. We have knowledge extracted from models, models deriving from data. So in the past, we have a lack of data and many models. And I personally fought with the problem of not having data to my ideas. And today we have the opposite. We see what's happening with PMUs, what's happening with smart meters. We have a flood of data, a set of data, and we don't have enough models to deal with that. That is a game changer. So we need to learn from data. And the state estimation process in a power system has similarities to a learning process. In fact, we try to tune up a model of the system that would provide me information about the system, estimations about the state variables, the voltages traditionally. And I have some performance criterion describing how good is the estimation, and I have an optimization algorithm that tunes the parameters in the system that is learning from the data. So this is very, very close to a learning process. And how do we assess the quality of the model? Well, ideally, the errors between what the model produces and what we measure or perceive from the reality, the errors should be close to zero. But is this true? I don't know. The fact is that after decades of almost stagnation, forgive me, those that have been working on this, but no really breakthrough happened. Now state estimation is on the rise again, because in the past, it was a static exercise, snapshots of the system. But today, it is expanding to distribution, and we see in the future that instead of taking snapshots, state estimation will make videos of what is happening. It will go into the dynamic domain and not only in the static evaluation. There are many reasons for that. One of them is that we have new devices, the PMUs, that offer tremendous possibilities in terms of frequency of sampling information from the system. Now, the PMUs are a game changer, as you will agree, because the frequency of sampling is on the order of milliseconds, while in the past conventional measurements, let's say roughly about 1 minute, sometimes 2 minutes, and that would be the sampling frequency. In many cases, at least for the useful information to be at the control center. So the combination of two systems that have very different sampling frequencies is not easy, but must be done, and it requires a lot of new approaches. We adopt a fusion approach because we believe that the best strategy for the transition in the industry environment is to keep the conventional model giving familiar results, namely doing state estimation from classical measurement devices, SCADA measurements, and in parallel add something else. I call it here a PMU model in red, add something else and provide a fusion process to obtain better or new results. But at the same time, because we kept the conventional model, we can still have familiar results for the operators. And we believe this has two advantages. Operators are not scared by just new results. They can see what their old trusted results, how they look like. And the company does not have to throw away all the software and things that they have in the company. They just need to add some models more. Now, when we have PMU measurements, what happens is basically this. You have at the control center SCADA measurement, then you have the PMU measurements arrive, and then you have another SCADA measurement. And what the PMUs are doing, they are acquiring a sequence of sort of photograms of the behavior of the system between SCADA measurements. Now, how to make these information compatible? That is what we try to answer. One of the answers is a work that we have been exploring. I will leave more details to the next speaker. But if we think about Bayesian inference, and I'm not going to spend time discussing Bayesian inference, but if we think of this, then we can develop a model where we have to estimate some priors. That would be in the order of minutes. That would be the SCADA measurements. And then between them, using Bayesian inference, we can estimate the PMU. We can include the PMU information and have as departing point the SCADA measure. But in fact, I'm going to concentrate my talk on this, how to build better prior models, and forget about the second part because this will be addressed in the second talk. If I go to the developing of better prior models, the fact is that we need very good prior models, very good models to estimate the SCADA data with the SCADA data, because this will influence all the estimations along milliseconds when you are receiving the PMU information, and you must rely also on the previous SCADA estimation. So if you don't have a good SCADA estimation, the rest is rubbish. The important thing to understand is that in an intelligent or training system, the information that gets input in the system from the data, the information not all goes to the system that we build, the model, but a part is stored in the error distribution. And this is the new point of view, is looking at the error distribution. And instead of thinking of Gaussian errors of the distribution, etc., no, we try to think of it as a Dirac pulse, a function where all errors would be equal, a distribution where all errors equal. If all errors are equal, then I can have a perfect predictor. It's just the equal error becomes a bias, and I just can add it to the result and have the correct result. But the important property of this distribution, like a Dirac pulse, is that it has minimum information possible. And to measure information in a distribution of errors, namely, we can use concepts of entropy. We are not using Shannon entropy, we are using Rennie's entropy. But entropy is a function that we can use to measure the quantity information. So the objective becomes to minimize the content of information of the error distribution, not to minimize minimum square errors, etc. And the other helpful concept is how do we translate from a discrete set of errors, from a discrete number of measurements, how we translate this into a continuous function. We apply the concept of Parson windows. To estimate, we put a Gaussian kernel around each point, each error, and the sum of these Gaussians divided by n, but the sum of these Gaussians gives me an estimate of the continuous function that would explain, it's hidden, but would explain these points in green, the errors that I have in the optimization. So an important detail to take note is that the size of these Gaussians matters. Size matters. And if you have a very large sigma, the estimation looks also like a Gaussian. If you have two small sigmas, you just have isolated pulses, and it's not interesting. Both are not interesting. Interesting is this one on the left. To see how useful this concept is, look at this time series or whatever in blue dots that you have here. You want to have a model for this, but from time to time you have an error coming, a gross error, outliers in fact. And if you estimate this using the minimum square error, the least squares traditional process, you get this dotted line as the model. But if you use another concept based on entropy that we call core entropy, here is a mathematical expression, then the result is this red line, ignoring the existence of those ones. And this is exactly what we want. We want a model when we have data coming to the control center that is corrupted by some bad data, and bad data could not only malfunctioning of devices, could be injection of malicious data from a cyber attack. We want to filter naturally those bad data and just do naturally this estimation. And we can do this with this type of functions. I'll give just one small example. You have here a toy system. There's a big error here. The flow should be from left to right on line from 3 to 4, but in fact the data comes as minus 0.12. If I apply the classical minimum square error to estimate the values, I get these values in red. This estimate the voltages, and then I get the flows, and the flows in red. There is some correction, but if I apply the new entropy criteria, or the MCC, maximum core entropy criterion, that with this function, where I see here the difference between Z, which are the measurements, and H is a function that describes the powers in the network from the voltages, then I get these blue values, and the blue values are, this is in the line, this is a very big correction, totally to the right 0.1, instead of that shy 0.048, and this is the correct result. And if I see the distribution of the errors, all errors are compactly around 0, and there's one very big error. That was the gross error that is identified and corrected, and this is what we want. And the first conclusion that we arrived is that playing with the sigma gives us a gross error detector, because if the sigma is very large, as I said, the shape it becomes similar to the parabolic shape of the minimum square error. So this is the same solution. But if then I shrink the sigmas of the Parson windows, the distributions of errors become very different. And this allows us to have a gross error detector, because if I start with the classical least square solution and then shrink the Gaussian function, the Gaussian kernels, if the result changes, there is a gross error in the set. If the result does not change, then the set is clean. So I have a gross error detector right away. We tried to develop a state estimation with this process, with this concept, using Gauss-Newton iterations. It is possible. This concept in this equation, first equation, is how we do iterations in the Gauss-Newton process from the classical least squares, weighted least squares, and we can arrange the same type of equations with different formulas, but anyway, it's the same type of equations for Gauss-Newton iterations over the new criterion. However, this is not so easy to solve, because sometimes this problem appears. You can see just a small example, visually illustrative, which is when we have very large sigma, we have the solution of the mean square error. The classical solution is there, but when we start putting sigma smaller and smaller and smaller and smaller from left to right, the solution that we try to calculate under the new criteria using Gauss-Newton iterations is trapped in that local optimum, and the correct solution should be in a higher, different hilltop, but it gets trapped there, so you get the wrong answer. So sometimes we get the wrong answer if you do this. So we developed a new approach, and this is the news of this talk, the challenging, provocative news of this talk. We developed a totally new approach based on combining two concepts, combining generalized core entropy for the kernels and interior point method as a solver. I'm not going into mathematical details of how we solve this, but this expression is the objective function. And here are the residuals of the state estimation. But this expression here inside the summation sign is the generalized core entropy that I will explain later. And we transform this into an equivalent model with objective function and constraints and solve it through the interior point model. And this gives us a solution. Now, why generalized core entropy? Generalized core entropy, instead of using a Gaussian kernel, uses a much broader definition with parameters, shape parameters, C. shape parameter. If C is equal to 2 in that expression above, then you have again the Gaussian function. But you can change C, and we mathematically demonstrated, this is absolutely mathematically demonstrated, that the optimal shape parameter to produce the best state estimation is C equal to 13.4. You may be surprised with that, but it is mathematically proven. So we have defined what is the best shape of the kernel to put in the objective function. And then we use the interior point method that is based on a central path concept, not approaching the boundaries of the problem. We proved also mathematically that using a neighborhood definition based on the Chebyshev matrix, L infinite, we have the best results for gross error identification when we combine an interior point method with an objective function that uses generalized core entropy. Now, to convince you of this advancement, I'm showing you some results. In the competition between the GCIP method, the new method, and the old method called the largest normalized residual test used to correct bad data in traditional systems, first processed with weighted least squares. This graph shows that we up to 5 simultaneous gross errors in the 30-bus system. The number of iterations is relatively steady, same number of iterations of the new method to achieve a result, while with the classic largest normalized residual test, it is growing, the number of iterations is growing with the number of simultaneous gross errors in the set. And this is an average on 500 experiments. Also, this graph shows you something else, which is that the method based on weighted least squares fails to converge in many cases. And it fails because there are cases where it cannot solve the problem. We have here tests for different redundancy measurement schemes, and 100% times our method worked, and the classical method failed to give an answer in many cases. And then, why is it failing? Well, because, I'm sorry, because leverage points, critical measurements, critical sets of measurements, that is not addressed by the classical method, the weighted least squares, but we have mathematically proven that we could use our new method to calculate the errors in that. So you can see that the missing gross errors with the classical approach with weighted least squares and normalized largest normalized test, the missing rate is high, and it is high because we have included in many of the data sets, we have included by randomly generating data. We allowed the critical measurements to appear, errors in critical measurements, errors in leverage sets. Also, you can see the false negative rates are very low. False negative rates, meaning that the cases where an error existed and was not detected are very low, or 100% of the cases. Just to convince you of that, I have here an image. You must believe in me, of course, but this image is from two gross errors falling on a critical set in the 118 bus system. This case was considered mathematically proven that could not be solved, and we demonstrated that it was mathematically proved that it could not be solved if you use the classical Gauss-Newton iterations and weighted least squares. If you use that method, you cannot solve this. But if you use the new method, then you can solve, and here is just a presentation of the results. It means nothing except that the true value is very well over the estimation. And this is absolute. The classical methods cannot give any result. It's not this or give with a big error. They cannot give any result. So this is quite a very good advancement. All the detailed information is published in these two papers that you can see there. So you can go and examine it for yourselves. And the importance of this new method is that now we have the possibility to generate very good priors of extremely good quality to start a process of using Bayesian inference for the PMU data. And so this is a very, very exciting advancement. And it is only even more exciting if we consider that after concentrating on the priors, the next talk will concentrate on how to calculate this. As a summary, a very stable method in number of iterations, always converging in all cases, solving problems that were considered impossible to be solved, better results than the classical approaches, and scaling very well for higher dimension systems. So please, I'm stopping for the moment. The story will continue with new episodes with the presentation of Professor Joan Bosco, London. And that's it, Professor Pesser Lopez. I return to you the control and perhaps some questions. Thank you very much.
Yes, thank you very much. Thank you also for helping to keep the time so well. So you keep it quite well. I would like now to see if there are any questions from the Q&A. I don't see any questions, but I would like to invite you to even to make your questions by raising the hand, and I will give you the micro. So who wants to be the first? Okay, so I have I have two questions from the Q&A. I'm going to just to read them, and then I will give you the hand to Niels and who else? Well, at the moment, Niels, please keep your hand raised, and I will pass you the word afterwards. So in a free of bad data measurement set, are there significant differences between the estimates produced by weight least square method and MCC? MCC avoid post-processing of identifying gross errors. Since there are changes on the model, the classical concepts of critical measurements and sets still apply?
Can I answer this, Robert?
Yes, please do.
Well, thank you for this question. It is first answer is that if there are no gross errors in the measurement set, the answer is exactly the same. The estimates are the same. One of the reasons is that when you put Gaussian or generalized Gaussian kernels around the errors, the tip of a Gaussian function looks like a parabola, and the MCC and the least squares is a parabolic method also. So if you want the Taylor's expansion of the Gaussian function, if you keep just the first terms, is also a parabolic term. So if you have just very small noise, the answer is the same, which is good and reassuring. But the minimum maximum core entropy avoids, yes, the answer yes, it avoids post-processing. The filtering of gross error is automatic, inherent to the model, to the mathematics of the model. So I don't need any post-processing, which is a big advantage. Post-processing methods have this drawback, is that their starting point is already wrong information, because the starting point is contaminated information from the errors in data. So we don't start from contaminated data. We just do it in one single step. The concepts of critical measurements and critical sets are very much related to observability of the system, but this concept is related to the the matrices that are derived using the traditional Gauss-Newton derivation from the weighted least squares. And so there is still some peculiarities about the critical measurements, but we have proved that with our approach that does not transform the matrices into that Jacobian matrix that you use in the classical state estimation, we have proved that you can calculate things about errors in critical measurements that you could not. In fact, there is a theorem that proves that you cannot calculate errors in critical measurements. However, the departure point of that theorem is the Jacobian matrix derived on the Gauss-Newton method. If you don't use that method and have our approach, those problems disappear and we can calculate. So there are leverage points and the critical measurements exist in some way. They have effects in the estimation. However, with our approach, we can address them.
Okay, thank you, Vladimiro. Two questions from Gil Sampaio. So how would the lower redundancy affect the method, and how suitable would this method be for distribution systems?
Well, we have presented one slide showing that for different levels of redundancy, the performance is keeping quite good. And in fact, in my view, we can expect better behavior than with the classical weighted least squares method. Why? It's because when you start reducing redundancy, in some way you start getting closer to the idea of critical measurements. You may have more critical measurements in the system if you reduce a lot redundancy. So you start seeing the advantage of the new method when you have lower redundancy. Also, if you have extremely large redundancy, a gross error gets more diluted than if you don't have such a strong redundancy. So in fact, when we have less redundancy, gross errors may be more dangerous for the interpretation of the system state. And precisely when we have more redundancy, that's when our method works better. And this answers your second question, because in distribution systems, in many cases, don't have much redundancy. So it is much, in my opinion, better for distribution systems. However, the complete answer to this is not just the simple method, but it is the combination of this method with the method that will be discussed in the next talk. That is what is really, really good for distribution system.
Okay, thank you, Vladimiro. Now I would like to allow some live questions, and I will start by Niels. Please.
Okay, can you hear me?
Yeah,
yes.
Okay. Yeah, first of all, thank you very much. This is Niels Bornhaus from University of Kassel. First of all, thank you very much for this very interesting presentation. So especially for me, it was very interesting because I only started with power systems after my PhD, and before I was working in the area of communication technology, and I digged into all this stuff in digital signal processing and also information theory. And now I see it all comes back. It was not in vain. It can be applied also to power system. So that was really interesting. And so my question is, in Germany, we have a little bit different situation in the low voltage and medium voltage, different than you presented in the beginning, that now you have such a tremendous amount of data. In Germany, in the low and medium voltage, we don't have that much data because we don't have a smart meter rollout yet, and we are dealing with very few measurement data. And for this case, we have developed an approach which uses artificial neural networks for doing the state estimation and estimating the missing data. My question is, it goes a little bit into the direction, I think, of the last question, the previous question. Is your approach also working for few data? Because that would be interesting to apply it also to our case.
Thank you, Dankeschön. But yes, with some limitations, as I said, it works much better with more information, always all estimations. The thing about smart meters on rollout is the following. This will happen tomorrow, if not today. So we are developing a system for the future, and there are large areas in Portugal that we have already deployed smart meters, and therefore the problem is, how do we get value from the investment that was done in all those smart meters? Because the devices are there. And in Germany, I'm sure that there are regions with smart meters, and they will be rolled out very, very soon. And you need to prepare the control centers for those data, because the big problem, and I believe in Germany as well, is when you have too much, for instance, photovoltaics injecting in the distribution at low voltage inclusively, and you may have strange values of voltages in the middle of the network, etc., depending on the hour of the day. You need to, the operator needs to know a lot more about what's going on in the system than previously, when it was just a top-down flow of things, self-regulated. And so actually we have in operation, also we tested and supplied for the Portuguese distribution company, also a sort of a state estimator using autoencoder neural networks, using the PMU, the smart meter information. So it's passed to EDP. Yet what we see is that alone is not, we can do better than that. Okay, so about the neural networks to predict, our approach has been using autoencoder neural networks, which allows us to predict missing signals, rebuild missing signals in the system. But we can do much more. I would invite you to watch carefully the next presentation, which is also very, very amusing.
Okay, thank you, Vladimiro. So we are running out of time, but still I would like to pass the word to João Catalão. This will be the last question, and I would like also to introduce you to a new initiative that we are starting at this webinar. So after this this presentation and the response to these questions, we will launch a poll with several questions, and you will have 3 minutes to answer them. But before that, I will allow also João Catalão to put his question. Please, João.
Professor, can you hear me?
Yes.
Very well.
So, good afternoon to everybody. Congratulations to Professor Vladimiro Miranda. Excellent presentation as always. It was not supposed to be a teaching seminar, teaching webinar, but we really learned a lot. Can you tell us a little bit more about the computational time or the computational efficiency of your approach? Because I was checking, you already have some citations, which is amazing when our works are already cited. And there is already a paper called Accelerated Generalized Core Entropy Interior Point Method in Power System State Estimation. So were you aware of this paper that you already said some citations? Does this mean that your method was not accelerated enough? Please, can you tell us a little bit more about computational time and computational efficiency? Thank you very much, and congratulations.
Thank you, João. I suppose, Catalão, you are calling from Barcelona. And the computational time in all our tests, competing against classical weighted least squares, plus the largest normalized residual tests post-processing, it was extremely competitive. Extremely competitive, and the more gross errors we have, then the times of calculation become faster, much faster in our approach than in the classical one. You saw in one of the graphs the number of iterations increase to clean up the data set when you have a large number of gross errors, but not in our approach. So in terms of industrial product, we feel absolutely confident that it just can be translated into a control center, and it will not harm in any way the computing times. But if there is now, this is news for me, I must keep track, thank you for informing, if they have now an accelerated, our method accelerated, so that's great news. So this is research. That's why we publish, and that's why people read our papers and go forward. And I am so happy. I'm going to check that reference, or you can send me to make my life easy. but the question is very, very, very clever. The computing time is a concern, but I can reassure that we are absolutely, for 0 errors, the computing time is basically the same for calculating estimation. So after that, we start gaining.
Okay, so thank you very much, Vladimiro. Thank you for this excellent presentation. And so for all the clarifications that you provided at the end, thank you.
Let me just say something. Ask the audience to answer the poll, which is very, very interesting to feel, look at my image, to feel the pulse of the community. It's very, very interesting. So please answer the poll.
Yes, so the poll is now being launched, and you have 3 minutes to vote for all the questions. So do it as...
Yes, it's multiple choice, but you don't have to choose only one. You can choose more than one in your answers. That's simple things. Oh, I cannot vote.
Yeah, you cannot vote. Too many questions.
Just one question. Very many options, but just one question.
Well, we see that we have some feedback. Some people are already voting. Okay, good. Very good. One more minute to go.
Perhaps you can tell us a small joke of your professional life to entertain the audience.
Well, when I see this, I always remind me that those TV shows where they are just inviting people to cook, and then they tell them 5 minutes to go, 2 minutes to go.
Okay, so you believe that the audience are the cooker, and
Yeah,
and you are Gordon Ramsay.
right. I will taste it at the end.
Very well. I believe that some of the answers to these questions will provide very interesting insight into the feeling of the community.
Definitely. Okay. And that's it. Thank you very much. I will sharing poll results. You can see the poll results.
Yeah, I can see that.
Okay.
I'm supposed to comment a little bit on the results. I'll comment on the first two questions,
but we are running out of time, Vladimir.
Yeah, so I'll be very fast.
Please.
It is the first point, the first question, relying solely on PMUs is dangerous. That is correct, absolutely. The GPS signals are controlled by military, and they have been tampered with in military conflicts. So if we risk to have a collapse in our power system, if there is a conflict somewhere else. So we need to pay attention to this. PMUs are too expensive. Not really true, because they are becoming very cheap. We see a drop in prices similar to, I don't know, photovoltaic panels or whatever. So very soon they will be cheaper. You can always trust PMU signals. No, you cannot always trust, because they are reliable, but not totally reliable. We have cases in several countries where there are failure rates from the GPS signal, from the transmission, from the electronics of the PMUs. So if you put too much trust in those signals, then when one fails, because you put too much trust, then you'll trust the wrong picture. And also, for my last comment,
please.
I agree totally that pervasive distributed generation and high penetration of electric vehicles will make state estimation a crucial function in distribution operation. I'm so happy to see that this opinion is largely shared. So these are my comments. Thank you very much.
Thank you very much. Thank you for your participation. So we will now go for the next presentation, and I would like to start by introducing Okay, so our next speaker is Professor Joan Bosco, London Junior. He got a PhD degree from University of São Paulo in Brazil, and he did postdoc studies at the Alexandria Research Institute at Virginia Tech, and also at INESC TEC. He's associate professor at University of São Paulo, São Carlos, Brazil. He's also researcher at INESC PND Brazil. He's an IEEE member, and he is also ad hoc advisor of FAPESP in São Paulo, and the CNPq, which is the National Council of Technological and Scientific Development for Brazil. And please, João, the screen is yours, as I said to Vladimiro. Please.
Okay. Good afternoon. Good afternoon here in Brazil. Good morning. Good evening, everyone. Thank you, Professor Joan Passos Lopes, for presenting my biography. I'd like to say that it's a pleasure to be here to talk about the research that I developed together with INESC TEC. And but I recorded my presentation, so I'd like to ask you to Joan to start, please. Thank you for being attending this webinar. Thank you, Professor Joan Passos Lopes, for presenting my biography. And I'm going to continue the story that started in the presentation of Professor Vladimir Miranda. And now I'm going to present the methods for including measurements with vastly distant sample frequency in power system state estimation, and also some simulation results. Let's start talking a little bit about the theoretical concepts. So the method proposed by our group in this contest are based on the power system static estimation model to estimate the priors, the forecast-related state estimation model to obtain the maximal a posteriori estimation according to Bayesian inference concepts. As Professor Vladimiro emphasized in his presentation, the estimation of the priors must be as robust as possible, that is, must be resilient to gross errors, missing data, etc. And because of this, nowadays we are investigating the use of good quality. As for example, the estimator based on the generalized coentropy interior point method presented by Professor Vladimiro. However, the preliminary results that are based on the use of the weighted least square to estimate the priors. The first approach that I'm going to present is a two-stage method for including PMUs in state estimation for a transmission system based on a state space model. This figure illustrates the updating time interval of SCADA and Pmu measurements. Observe that between two SCADA data sampling, there are several PMUs data that can be used for state estimation, but not at the same time. The estimation process in each stage initializes as soon as the respective measurement sample becomes available. So, when a SCADA sample becomes available, stage 1 is initialized and consists of the traditional nonlinear static state estimation model to deal with the SCADA measurements and builds the prior evaluation of the state variables. When a PMU measurement or sample becomes available, stage 2 is initialized and consists of using the Pmu measurements to update the posterior distribution obtained according to Bayesian inference concepts. Okay, so in order to give a more details about the proposed procedure, let's analyze each step of the flowchart illustrated in this figure. Then, when a SCADA sample becomes available, stage 1 is initialized, and its solution is the estimated state and its respective state covariance matrix. After that, when a Pmu sample becomes available, stage 2 is initialized. The first step is to build the state space model, and the next steps are the solution of the problem and the updating of the state variables. Based on the Bayes theorem and on some assumptions, this linear system results on the estimated state of the second stage. Note that the matrix of this linear system is a positive definite and full-rank matrix, since the previous observable SCADA stage gain matrix provides the covariance matrix of the forecasting error. Therefore, the unique requirement for the proposed method provide an estimation is a SCADA observable system. It's not necessary that the system be Pmu observable, okay? And this is a very important characteristic, since the number of PMUs is usually insufficient to provide full system observability. When new PMU samples arrive, stage 2 is executed again, considering the same prior distribution. Stage 1 will be executed again only when a new SCADA sample arrives, okay? This figure illustrates the state space model of the proposed Bayesian state estimator. We have here the first stage, the static state estimation using SCADA measurements. And here, the second stage that consists in updating the state using the Pmu observations as they become available by the posterior distribution obtained by Bayesian inference. As previously presented, the first stage sets the prior distribution, as the estimation provided by SCADA measurements, and it keeps it fixed while new PMU samples arrive. Okay? These figures emphasize the difference between the Bayesian network proposed here and the Kalman filter. Okay? Observe that the Kalman filter is the recursive version of the proposed Bayesian approach, where the prior belief is updated as the last posterior estimation. It's important to emphasize that the intention of breaking this recursive chain is to obtain a state estimate more sensitive to system changes, that is, to non-stationary conditions. The second method that I'm going to present in a summarized way, okay, is a three-phase distribution state estimator based on a Bayesian inference approach to manage different sample rates of typical source of information presenting distribution networks. The proposed method is based on a Bayesian fusion procedure to deal with different kinds of measurements and their different temporal scales with the concept of sampling layers. It is an extension of the two-stage method previously presented, but now the measurements are separated in more than two subsets. This according to their respective sampling rates, forming a sampling layer or forming sampling layers, which is characterized by a common updating time interval, as indicated in this equation. This figure illustrates a typical location of different kinds of measurements in distribution systems and the respective sampling layers according to updating time interval. There are 4 sampling layers. The first, sub-measurement layer. After we have the smart meter layer, SCADA layer, and PMU layer. The estimation process in each layer is initialized as soon as the respective measurements become available. The state is updated by a maximal a posteriori estimation given by this equation that is similar to the method previously presented, but now considering the concept of sampling layers. The estimation result of each layer is then used as the prior distribution for the state variables in the next layers. We have here a hierarchical model, Bayesian hierarchical model. Here we have the probabilistic network representation for the multi-layered posterior estimation to deal with measurement with different sampling rates. Observe that each sampling layer deals only with measurement formation from its group, and the final estimates made available for the following sampling layers. Now, this figure shows that the slower layer sets the prior distribution and it keeps it fixed while new samples of the faster layer arrive. Okay? So now I'm going to present some simulation results. The first performed considering the IEEE for the bus test system test case, considering with the metering system illustrated in this figure, we have SCADA and Pmu measurements. Observe that the blue area is not Pmu observable, but all the system is SCADA observable. Monte Carlo simulation were performed with 100 repetitions. In this test, it was simulated a fixed load scenario for the network during the interval of the 60 PMU samples. This figure shows the mean absolute error index for the SCADA prior and PMU posterior stage for each state variables per bus. This for the voltage real part and here imaginary part. Okay? As illustrated in this figure, the posterior stage in blue reduces the estimation error. And I have to say, it's important to say that this is the essence of Bayesian inference. That is, it improves inference giving new observation, in this case, from the PMUs. Such reversion occurred even at buzzes that are not observable by PMUs. The buzzes emphasized here, buzzes 10, 11, 12, 13, and 14. This is because the prior distribution has correlation values, okay? The second test was performed considering the Brazilian real feeder from the city of Londrina, Paraná, Brazil. This figure represents the real feeder analyzed in blue, along with the location of the pseudo measurements and SCADA measurements. So this feeder comprises 1,058 three-phase medium voltage nodes. It is mainly monitored by pseudo measurements from typical load profiles every 50 minutes, and has SCADA measurements at the substation and the entire closer with updating rate of 1 minute. In order to validate the proposed estimator, independent measurements were taken in 3 different transformers, emphasized here, to compare the estimated results with the measured. This table presents an accuracy comparison between the Bayesian fusion estimator and the previous result obtained by a real-time load estimator available at the distribution management system of Copel, the utility, okay? With respect to the final voltage magnitude estimates. The results show the Bayesian fusion, the values, Bayesian fusion estimator enhance the estimation. But it's important to emphasize that the lack of measurement, of real-time measurements, limits the accuracy of the estimation process according to the pseudo measurements quality. That is one of the main challenges for state estimation in current distribution systems. This table presents the process time and the number of iterations of the weighted least squared state estimation process in the test feeders for each stage, stage 1 and stage 2. These values show the proposed Bayesian estimator presented an adequate process time for real-time applications, okay? The next test considers the IEEE nodes test feeder, and this table presents the respective metering system and the associated sample layers. Here we have the sampling rates of each sample layer. It's important to emphasize that only the pseudo measurement sample layer is fully observable. It was simulated a stationary condition, that is, a fixed nominal loading along all observations. And here you have the mean absolute error performance index for the estimation in each sample layer from the 3-phase state variables in each node of the system. In blue, we have for pseudo sample layer, in orange smart meter, in red, in green SCADA, and in red for Pmu sample layer. Analyzing the figure, it's possible to observe an increase on the state estimation accuracy for all nodes as faster samples are processed, okay? In the next test, it was considered the IEEE 123 nodes test feeder, and the matrix simulate is formed by SCADA and Pmu measurements located at the substation and at voltage regulators and switches, pseudo measurements in all nodes, virtual measurements in all zero injection nodes, and few smart meters at 8 nodes as special consumers. In this test, the Bayesian fusion distribution system state estimate proposed is compared with a hybrid distribution system which processes all measurements in a single stage via the weight least square algorithm, and also with an extended common filter. 2 load scenarios were simulated. The first one is stationary condition of fixed load values, and the second with 2% load variation and subtle load increase from t equal to 9 seconds to 50 seconds, okay? Observe that, okay, just I'd like to highlight that here we have the mean absolute error and here the time, okay? So observe that the common filter approach in orange, okay, in orange present a very good estimation for the fixed load scenario, but lost its accuracy in the presence of load variation, especially for a subtle load increase. On the other hand, the hybrid approach in blue, okay, in both graphs in blue, loses accuracy whenever load variation is presented, since it essentially mixes measurements, all kinds of measurements from different states in the same set. And the proposed Bayesian fusion in green keeps its accuracy level even in the case of a subtle load increase, showing better results in the presence of load variation, okay? And the latest test of this presentation that I'm going to present in this presentation was performed considering a full deployment of smart meters in the IEEE US low voltage test that has 342 nodes. This test was executed considering the SCADA measurements are located at the substation and feeders base, while PMUs measurements are at the high voltage nodes. And despite the distribution system being observable with the smart meters considered at the low voltage nodes, a pseudo measurement layer is kept. This because based on previous day information to accommodate possible loss of communication. This test validates the proposed method under a model that comprises all parts of a distribution system, from the high voltage substation to a meshed low voltage circuit, and the typically associated measurements. So this figure presents the temporal behavior of the estimated voltage magnitude at phase A of one of the low voltage nodes. In black, we have the reference values, and in orange, the estimated values, which were simulated the following scenarios. One, a normal condition with load variation of 0.5% for 2.5 minutes. Scenario 2, a momentary load increase to simulate a distributed resource variation. 3, a medium voltage feeder contingency, where during the first 30 seconds the network model is not updated with the topology momentarily incorrect. So we simulated here a case of topology error. And 4, the same contingency, but now with the updated model. Okay, so the topology error was detected, identified, and corrected. So the effect of the generation intermittence in scenario 2 in purple is properly assessed even though the smart meters update their values in each minute and not in each second. Okay. Only during the event span in scenario 3 in red, the distribution system, the method proposed loses its accuracy, showing the negative effect of unmonitored contingencies. During this event, the problem is the network model, as a case of topology error. It's not in the measurement values, okay? However, we are working in another aspect of the Bayesian perspective, that is the credibility intervals that provide a direction of state change and detects an anomaly in the system from the disagreement between the network model and measured values. So using these credibility intervals, the proposed approach detects the anomalies, but it's not possible yet to identify the anomaly, but the proposed method detect. So the last scenario, after a proper update on the model in scenario 4 in green, the proposed estimator regains its accuracy. Okay. So in conclusion, we now have the following: a Bayesian inference approach to perform information fusion in power system state estimation based on a sample layer concept. Comparison with the hybrid and the common filter estimator demonstrate the advantage of treating each sample layer independently without mixing information from different instances. And the proposed distribution system state estimator enables the detection of events even at the low voltage networks with the concept of Bayesian credibility intervals. And the practical application in a real feeder validates the proposed approach with current traditional distribution system feeder. And as future works, I emphasize the use of generalized coentropy interior point method to generate priors of good quality, and also the probability interpretation of the credibility intervals to enable their integration with different identification methods. Okay? So that's it. Thank you for your attention. And also I'd like to acknowledge the financial support of PAPESP, COPEL, CNPq, and INESC TEC. Thank you.
Thank you very much, João Bosco. So we will proceed in the same manner as before for the previous presentation from Professor Miranda. So there are some questions from the Q&A, at least one, but I also would like to ask the attendees to raise your hand and put your questions. So, but let's see first the question from the Q&A. So there is a question on slide 24 to confirm the understanding where the contingency update model 60.8 will it recognize the credibility intervals? If yes, that means the updated model will automatically simulate a new mesh layer until it achieves the most nearest approximation. Will this repeat 100 samples? So this is the question.
Okay. Whether the contingency update model will recognize the credibility intervals. Yes. Let me open the presentation here. I think that is better to show. Just a moment, please. Okay. So it's possible to use the credibility intervals. We have the analysis is not so simple. It's necessary to see if there is some intersection between the intervals of a previous stage and the other stage, but it's possible to do that. I think that in my presentation, let me enter, okay. I think that the details are in the article that we have published, but I'd like just to show here. Sorry, let me see, it's the last one, no? Okay, this. Okay, in this presentation, I didn't show the the intervals, just the state estimated, okay? But it's possible to see with another kind of analysis that it's possible to compare the correlation, the intersection between the variance of the prior estimate with the variance of the posterior estimation. And with this is possible to do a test, and with a probability, okay, of success. So it's possible to see if the change in the measurement is because of an anomaly, okay? So, but I don't have any figure here to show this in a more appropriate way, but in the paper, we have this type of explanation in a better way, okay? What's the order? Okay.
Yes, you have another question. Is hardware ready to implement the described methods?
Yes, we have implemented, for example, in the test that we performed with the Brazilian real feeder, we have implemented the method. Observe that in the current distribution system, we have a limited number of real-time measurements. So in this case, it was used just 2 layers, pseudo measurement and scalar measurements. But this is already implemented at the COPEL, okay? But the new ideas with the smart meters, with PMUs, we have implemented just only in the academy field, okay? But using a lot of this actually also this Brazilian real feeder, but not with real measurement, okay? In a simulated behavior.
Okay, thank you. Can you stop sharing your screen, Joan Bosco?
Sure.
Okay, so are there any questions that from the audience, live questions?
João, do you allow me to say a comment?
Yes, please do.
On this last question on the hardware. My comment is the following. That is a very interesting question because there is also a game changer in hardware for processing scientific calculations, namely in the sensors, which is extensively adopting graphics processing units, GPUs, to do these calculations. And it has nothing to do with the mathematical and conceptual method in some way, and yes, it has also, because we need to transform the method so that it can be put inside the graphics processing unit. But the acceleration, if you are successful in implementing inside the graphics GPU, the acceleration may be tremendous. And in my view, this is what will happen in the future when we have this near real-time processing of state estimation following the dynamics of the system, not only snapshots as in the past. We will need very fast processing, and I believe that adding to the equation, adding implementations inside GPUs will be the future. Thank you, João.
Okay, thank you very much, Vladimir. So, Joanna, we will now launch the poll. Can you start it?
Again, it's the same poll.
It's the same poll.
It's the same.
It's the same poll.
But we are sharing the results right now.
Oh, okay. We are sharing the results. Anyway, if Joan Bosco wants to just to comment any of the results, you are please invited to do it.
Okay, I'd like to say that when this new technology, PMU, starts to be used in state estimation, in the state estimation process, some researchers believed that it was necessary more state estimation because PMU is correct, no problem. So with the time, we have seen that this is not correct. So it's necessary also the state estimation process with these new technologies okay? And nowadays, because it's not possible to do the state estimation only with PMUs or only with smart meters. So this is the reason of our research in this talk, that is how to treat different kinds of measurements to do a good state estimation. You know? And so I think that the way to treat, I like the way that we start to do that. I think that the first results are really interesting and is a kind of technology, of method that can be easily implemented in the company. And but we have now to concern about the priors, how to generate good priors. So this is the reason of here in Brazil we are starting to using the method that Professor Vladimir is working, and I think that it's a good way to treat. And I think also that different kind of measurements maybe will be necessary to use different kinds of approach. Okay, just this. Thank you, Professor Joan.
Okay, thank you very much. I want to thank you both for the excellent presentations you did, and I would like to invite all the attendees to attend the next webinar, and also keep watching the program of webinars that we are presenting, and we will be happy to have you on the coming webinars. Thank you very much to all of you.